We are now in Unit 2. Unit 2 actually just an example design. We are trying to demonstrate how you are going to do when your job is to design a chip. Okay? And we use the CPU as an example. One step we are going through. And eventually you can get a functional chip for the CPU. We have already finished this. And last time I mentioned that it's just like programming, just like software engineering. There are many good features you probably should follow to make a good design, including hierarchy, regularity, modularity, and locality. I'm not going to go through again. And based on the goal, based on the requirement for design, you might, usually we will try to design, doing design partitioning. It's a top-down process, top-down design process. Just like programming. Top-down design. So, starting from architecture, given that we are going to design the CPU, what is your architecture? How do you define your CPU? So typically, it's from user's point of view. What does the chip do? So, for example, we're designing a main CPU. You need to define your instruction set, right? Based on the instruction set, you can write your program in the CPU. So, and how many registers do you have in the CPU, in the system? There are many kinds of CPU in industry, like IBM, x86, Alpha, okay, ARM, so on and so forth. So, given the architecture, after you design the architecture, we try to get it down from the top level, and then the level below that, keep going down until you finish your design in physical layout. So given the architecture, we try to design the microarchitecture in the architecture. So what kind of CPU do you want? A single cycle, or multi-cycle, or parallel machine, or small scalar? Okay, we are not going to talk about the detail of the CPU design, but just to give you roughly a design goal like this. And then after you define the microarchitecture, we try to design the logic block, logic gate, logic circuit, how our functional unit, functional block constructed. Okay. For example, given an adder, what kind of adder design you want to use? Either ripple carry adder, or carry loop adder, or carry select adder, so on and so forth. There are many kinds of adder design style or adder design approach. And after that, get into the block. What is the circuit? Given the logic you come up with, what is the circuit inside? How are transistors used? How are transistors connected to realize the logic you want? So you might use complementary CMOS gate, you might use patch transistor, you might use domino logic. This is for high-speed circuit. We'll talk about that later on. After that, then that's the bottom layer, the physical layer. That's the chip layout. Okay? The chip layout for their pad, the chip layout for memory, for random logic, and so on and so forth. After you finish the layout, that's the final design you're going to finish. And then you send the layout file to the foundry to manufacture the chip. We typically say that with the term tape out. Tape out means that we send the layout file to the foundry, like TSMC, to manufacture the chip. So typically it is a top-down design, right? Starting from high level and reaching the bottom layer, and you are done. And you might find that in middle something wrong because maybe it did not make it correct. Maybe it's not good design on the high level, and when you reach the lower level, you find that you are not going to meet your requirement. You are not going to reach your focused goal, something like that. You have to go back to redesign and then do that again. Any question? So let's say we are going to use the main CPU as a design example. The main architecture in here, we are going to use a subset of main processor architecture. So only a subset of the instruction set will be realized. And we take that example from the textbook on computer architecture by Peterson and Henderson. You might have already learned that before. MIP is a 32-bit architecture with 32 registers, but it's going to be too complex. So we try to simplify the design. We consider 8-bit subset using 8-bit data path. Full length should be 32-bit, but in this simplified design, it's going to be 8-bit version. And we only implement 8 registers instead of 32 registers, from R0 to R7. And R0 is all hardwired to 0 value. You cannot write data into R0 because the value already fixed at 0 value. And also the point counter is going to be minimized to 8-bit only, not 32-bit. So we are going to design this version of the CPU. Another subset of the instruction set of the mid CPU. The full instruction set is much larger than this, but just for example, add, subtract, and or set less than, add immediate, BQ, jump, load byte, and store byte. Here is not load word or store word, but instead load byte because it's the 8-bit version. Based on the instruction set, we try to design the CPU. It's also part of the instruction set architecture. The instruction format has 3 kinds of instruction format: R-type, I-type, and J-type. This is the different instruction format with the field, okay? The opcode here, the register A, register B, register D, or RA could be RS, RB, RT in the textbook. In the function control, the unidivided system bit is the jump destination. And based on the instruction set architecture, you can write your program on the machine. This is the execution program, which is Fibonacci sequence. You might know this Fibonacci sequence is a sequence of numbers starting from 1 and 1, and then adding the previous 2 numbers become 2. Adding 1 and 2, 3, 2 plus 3, 5, 3 plus 5, 8, 5 plus 8, 13, so on and so forth. So that procedure is to generate the number of the Fibonacci sequence. So just to give some example of execution program. And compiler try to translate the execution program, the high level program, into assembly code. Looking like this. The assembly code for Fibonacci sequence. With the sequence of instruction, add immediate, the BQ, the subtract, add, the jump, loop, and then store byte. So there's a loop here. So this is a typical assembly program. after the assembly code, you can translate the assembly code to machine program. For example, for each instruction like ADDI, add immediate, R3, R0, A, meaning we are adding R0 and A, we put a result in result 3. So how do you translate the instruction, assembly instruction to the machine code? Well, based on the instruction format, we know that ADDI is an I format. So try to look up the spec. What is the opcode for the ADDI? So put a -3 in here, 8-bit. And the RA is R3, so 3 is here. So 0 is here, and then A is here. So that's going to be your memory code for that specific instruction. So that way, you can try to translate for each assembly instruction, and eventually you're going to get the machine code like this. It's an assembly program, and then machine code. That's the machine program in memory. The CPU is trying to decode and execute. Any questions so far? And now we are getting into the hardware design. Given that we are trying to design a multi-cycle machine, it is a multi-cycle machine for the instruction set we define, and then we come up with this architecture. This is the point counter here, the point counter, the multiplexer, the memory. It accommodates both instruction and data. So this is a shared memory, including the program, including the data. And these are the registers. That's the instruction. Point counter send the address, you fetch the instruction, and that's in here, 8-bit, okay? I'm sorry, 32-bit. But in here, because it's an 8-bit version of the CPU, but still, instruction is still 32-bit. So we need 4 clock cycles to fetch one full instruction. The data path only 8-bit. You need 4 clock cycles to get a full instruction in the register. And then you can decode it. The opcode is going to be sent to control unit. It's going to generate another control signal to coordinate all the functional units in the data path to realize the instruction, ADDI or any other instruction. And this is the finite state machine for the control unit. The control unit is here. Control unit is a communication circuit that accepts opcode, and also it keeps track of what stage the instruction is in. And then it's going to generate many control signals to control all the behavior, all the operation of the data path. So in the finite state machine here, each state represents one state, represents one clock cycle, represents one state of the CPU. These are no signal value that should be asserted or should be set to a certain value. So 4 clock cycles to fetch one instruction, 8-bit, 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 and then 32-bit the instruction. And decoding instruction, okay, these are required control signal value. And then depending on your opcode, it could be low byte, store byte, it could be like the low, this is going to be, okay, this R-type instruction, it could be like branch, could be jump. And eventually, if that instruction is finished, you go back to fetch the next instruction, and so forth, likewise. Now, what should be the logic design? You might be faced with many choices. So, given that we are designing a CPU, so this is a CPU chip. This is the outside circuit for the clock, and reset signal. This crystal oscillator, 行振荡器, and after the two-phase clock generator circuit, it's issuing two-phase clock. Well, actually, in industry, nowadays, people typically use single-phase clock. Although our textbook uses two-phase clock, but nowadays, single-phase clock is more popular. And this is reset circuit. The VDD here, the switch, the resistor, and this one, and connect to the reset pin. So can you understand the circuit here? Why that provide reset for the circuit? What does that mean? This circuit, if you did not push the button, press the switch, then this is 1. So this should be 0, right? Because there's no current going through the resistor. There's almost no voltage drop. There's no voltage drop, so this 0 is also 0 volt, signal 0, so we do not reset. After you press the button, after you press the switch, then it comes to the VDD, so there's going to be current going through the resistor. And then most of the voltage drop will be here, and this is going to be signal 1. That will trigger the circuit to reset the whole chip. But what does that mean by reset? What does that mean by resetting the chip? Anybody know? When you reset the chip, inside the chip, what is going to do? Yes?
Counter is set to 0.
Okay, yeah. That's an example. If there's a counter in the new CPU, it's going to be reset to 0 value. Actually, when we reset the chip, it means that we put that chip in the initial state, alright? Including that one counter, 0, such that it's going to fetch the instruction and location 0 in the memory. Okay? And also, for the other register, what should be the initial value? That signal reset is going to set that each and every register or flip-flop to the initial state. Most of the cases should be 0, but maybe the other value doesn't matter. When the chip wants to start from scratch, start from the initial state, we set 0 value, or we set a reset signal to 1 to start the chip. And this is the outside interface. The CPU connects to the memory. Sometimes we can put part of memory in the super chip. Yes, it's possible, but that's okay. In this case, the memory is in the outside, internal memory. We have 8-bit address issued to the memory. We read data 8-bit from memory to CPU, or write 8-bit data from CPU to memory. And these two are the control signals. Memory read and memory write. These two control signals are coming from the control unit of the CPU. Here. Control signal, read and write here. Memory write. And the memory read. Okay, in here, it omits the memory read. It doesn't matter. Some design have memory read and write. Some design simply memory write. If the memory read is not really necessary. And then we try to plan the chip design, given the space, given the plan. How do you organize? How do you draw the block diagram, roughly, or the interface? So we are going to have a data path in here. What is data path? This is data path. These are the data paths. These are control. So assuming that the data path is the control or controller. There's an ALU decoder, which is part of the control unit, but that's in charge of generating the signal to the ALU. If you look at the Pearson book, they indeed is an ALU decoder, which can be viewed as part of the control unit. So, phi 1, phi 2, the control signal, the clock signal, okay, two clock signals going here, this signal going here, the address going to memory, write data to memory, memory data coming from memory. And we have opcode. When you fetch the instruction, the opcode is going to be sent to the controller or control unit to decode it and then generate that control signal to orchestrate, to correlate the data movement or the data computation. This zero flag is reflecting the ALU condition. If you do some suppression, if they are equal to each other, and the result 0, it's going to give you 0 signal. That will decide some instruction behavior that branch EQ instruction. And okay, the function control for R-type instruction, this A bit will help decide what kind of operation for the ALU. Okay? This 3 bit controlling the ALU doing a specific operation like addition and subtraction. Anyway, you don't really have to understand the detail. Fine. Just give you some idea what we are going to do for a given project. And then we are trying to go down. Hierarchical design. Given the root chip, this goal, the system, we divide it into 3 modules or 3 parts. Control unit, controller, the data path, the air control, 3 different modules for the chip like this. Data path, controller, air decoder or air control. And then both the controller and air control need to use some computational circuit, and that can use the standard cell library. If you are trying to do a design using cell-based design, the library will provide all kinds of layout for the gate or for the PLA. So you can simply going to look at the cell library and use that circuit for your control and control. For that path, in the example, we are using this design style, meaning given a bit CPU, the bit design style means that we only design 1 bit data path, and you can put 8 copies together, try to try to get the 8-bit data path. So we are going to show that in a few minutes. For the 8-bit slide, it might have ALU, inverter, flip-flop. This is for RAM, for memory, the VLSI slide. It's for 1 bit, only 1 bit. But any kind of gate or flip-flop, you might need some even smaller component, like the adder, 1 bit adder, like OR gate, 2-input OR gate, 2-input AND gate, 4-input multiplexer, so forth. And for the OR gate and AND gate, the OR gate needs a 2-input NOR gate and an inverter. For NAND gate, 2-input NAND gate, you need an inverter and 2-input NAND gate. So some components can be shared. You can have many copies, significant the inverter gate, the layout. They are going to use the O2 and N2. And multiplexer, 4-input, is simply use 2-input multiplexer to control 4-input multiplexer. They might need tri-state switch, so on and so forth. So how do you design the system? Based on cell-based design approach, you might want to use HDL, high hardware execution language. The HDL in industry, there are two languages made of HDL. These two are most popular. In Taiwan, more people use Verilog. In the US or in Europe, more people use VHDL. They are widely used in logic design. So this is called cell-based design. Cell-based design. Meaning you don't need to draw the circuit, to draw the layout. You don't have to draw the layout by hand. Simply write the code looking like C language. Okay? And that code describes your hardware. And the software package like synthesizer, they are going to translate your code into the circuit for you automatically. You don't really have to get into the detailed circuit transistor. No, you don't have to do that. Simply write the code. So in the next unit, we are going to cover testing and the Verilog. Okay. Describe hardware using code. The purpose is it can document logic function and also simulate logic before building. You don't have to build a real circuit immediately. Before that, try to simulate your design. After you make sure that, okay, there should be no bug, then you can realize you can implement the chip, implement the system. Using synthesizing code into gate and layout. From the code, from the language program, from a high-level language program, you can translate, you can synthesize into the circuit. That would be much easier and also reduce the design time. But as I said, it requires a library of standard cell. Okay. The cell layout is available in your design that could speed up your design process. For example, is a Verilog code for 4 adder, 1 bit 4 adder. What is 1 bit 4 adder? Look at the figure here. This small circuit receives 3 inputs, A and B, and carry in, C is carry in, and generate 2 output signal. A is sound, C is carry out. Okay? Like this. If you got A, then 0, 1, 1, and this plus. It's something like that. You're adding for each bit position. Here, 1 plus 1, you get 1. And carry out, you're going to be 1, right? And then you add that 0 and carry out is 1. And then 1, carry out is 1. So for each bit position, there are 3 inputs. This bit, and carry in. Okay? The bit you generate from the bit position on your right hand side. A and B, 0 and 1. A, B, and this carry in. This 1 and this is C. And you're getting 2 outputs. One is the sum is 0 here. Sum. Carry out one here. So this is A, this is B, okay, and this is C carry in. You generate sum and carry out. Right? For each bit condition, you need one for adder. So how do you write the code? How do you write the variable code for this small adder? So just like C, module, just like function or procedure, the keyword module, for adder, that's the name for this circuit. And parentheses is a list of parameters, list of the input and output. So input signal A, B, C, A, B, C, 3 bit. Each variable 1 bit. And output S sum, C out, carry out, right? 3 input and 2 output. Then we try to design that for adder. So how do you design it? There are 2 parts, right? Inside, one is for generate the carry out. The other one is for generating sum. For sum, we use the equal gate. Is that right? 3 input equal gate because only when they are even, they are odd number of 1, you are going to get 1 for the sum, right? 0, 1, carry in 1. So the even number of 1, so the sum is 0, not 1. In carry out, if there are more than 1 bit is 1, you're going to generate carry out. So anyway, we can simply write down the Boolean function, and then you can write the code based on the Boolean function. So here, sum is a variable for the output. I'm sorry, sum actually is the sum module. Inside each module, you can have some module, just like calling function or calling procedure. Sum and carry. This is a module for carry. And the module for sum is not here. Okay, fine. For carry, this module is for describing this procedure, this function. C1 is a carry module. The carry module is a circuit like this. Input A, B, C. Okay, A, B, C. Output C out. Here, I'm sorry, here. A, B, C is the input, carry out is the output. Assign is the statement, the keyword for the variable. Assign C out equals A and B, or A and C, or B and C. In terms of Boolean function, C out equals A, B, or A, C, or B, C. Is that right? Yes, it's right, because if there are 2 bits, at least 2 bits are 1, you're going to get a 1 for carry out, right? 进位嘛，对不对？至少2个1加起来一定会进位，3个位元相加，至少2个1，那一定会进位。所以就是 A and B, or A and C, or B and C. You don't need A and B and C because it's going to recover this equation over here. So this is a typical variable code for the conventional circuit. And here is the adder. And then we go down in the top-down design process. How should logic be implemented? We mentioned this before. NAND gate and NOR gate versus AND gate and OR gate. As I said, actually, AND gate is composed using NAND gate and also inverter. OR gate is composed of NOR gate and inverter. So typically, NOR gate gate, NAND gate are simpler than AND gate, OR gate. And you need to consider fan in and fan out. How many input, okay, pin for the gate, and fan out how many for each output pin, how many is going to be used for the following gate, the fan out. And also, as I mentioned before, how wide should the transistor be? We are adjusting the transistor width such that the circuit speed can meet the requirement. For example, for inverter, the PMOS and NMOS transistor for inverter, if we want to have drain time and falling time about the same, then PMOS transistor should be twice wider, right? To compensate the mobility of the hole is only one half of the mobility of the electrons. Okay? So this is called transistor siding. Transistor siding meaning we are adjusting the length and width such that they can give you the circuit speed you want. These choices affect circuit speed, and chip area, and power consumption. And these three are key design measures. Circuit speed, chip area, and power consumption. We usually want the circuit speed as high as possible. The chip area as small as possible, and power consumption lower, hopefully is lower power consumption as possible. And logic sensors make these choices for you. Nowadays, many design steps are automatic process. You don't really have to get into the detail. Instead, the software will try to help, try to aid your design step. Like logic sensors make these choices for you should be good enough for many applications, such that you don't really have to hand design the layout. It's too slow. Using the tool can speed up the design process. Although it might not give you the best circuit, maybe not the fastest, maybe not the smallest, but typically should be good enough. Handcrafted circuits are still better, but the different narrow and narrow. They are not too much different from the performance in the chip area and power consumption point of view. Nowadays, however, for very high speed requirement, for very small chip area requirement, some people still prefer handcrafted layout. It's called full custom design. Handcrafted layout. Okay. Maybe less than like 5%, something like that. So again, the adder design for 1 bit, they carry out. This is a typical Verilog statement, okay, to realize the Boolean function. And this is the circuit. Okay. A and B, A and C, B and C, and all together, right? If we design this Boolean function using logic gate, look like this, and we can draw the whole Boolean function in one compound gate. It's going to look like this. It is a gate. But you might observe that, well, it's not really the complementary static CMOS gate, because we mentioned that before. In the A port down network, when A and B in parallel, it should be in series. When it's in series, it should be in parallel. But it seems that it's not the same design style. They are simply similar circuit structure, circuit connection. Well, in here, both versions are fine. Okay. What I'm saying is that A and B is in parallel. Typically, in 4-arm level, they should be serial. Yes, that's correct. But in some function, they are equivalent. Okay? They can be designed like this, and they are equivalent to the version from our design process from before. A and B will be here in serial. With C in serial, then here should be in parallel. Fine, that's also correct version. But this one is also correct. So then you might want to measure how many transistors you need and what is the gate delay, such that you can estimate your circuit speed and your chip area. And unit assigned is a high behavior modeling, meaning you can describe power from the high level description. You might also consider the gate level description like this. Module carry input ABC, output carry out. Wire SYZ. SYZ is temporary, is an internal signal point. This module has AND gate here, AND gate here, and AND gate and OR gate here. Both versions are fine. Either this one or this one, they are legal, they are correct coding for the carry module. But they are in different style. Behavior model, this is structural modeling. So in here we have AND gate G1. This one is G1 gate. The AND gate is a standard gate provided by the library. You don't need to describe AND gate or gate. They are built in the primary gate. Okay. For G1, it says that S is the output, AB is the input. Typically, we list the output first and then the input. G2, Y is output, AC is input, so on and so forth. So these are three AND gates. The OR gate here, G4, output is C out, input is SYZ. So that description actually describe how you connect these gates, right? Based on the statement here, it corresponds to the real circuit connected like that. In structural level design. You can even go down to the transistor level. But nowadays, people don't use the transistor level named very low. No, actually no. It doesn't make too much use, or it's not very useful. If they want to simulate for the transistor level, they are going to use SPICE to simulate the circuit behavior. So skip that. Although, yes, it provides the simulation or the description for transistor connection like this. But in practice, people don't use that. It is SPICE like this. As I said, nowadays people use SPICE to describe each transistor like this, and also the connection, and also specify the width and the length. W width, L is length, and also specify the drain and the source, the geometry, and then based on that, they can simulate the circuit behavior. But again, unless you want to look at the detailed circuit behavior, you don't really need to go through that nowadays for service design. let's take a break.
最后一张图要讲什么？
这个
对啊，
他们会用 Spice 去做电机
，Spice
一个软体，
哦，你是制定的 program，这个另外 language 是吗？
一个程式。
这是一个新的语言。
算我不知道说的语言，我知道那个程式叫 Spice。就很像这种模拟的程式的名字，这是一个名字，对。
你这样子每天骑视讯，真不累？
嗯？
你这样每天骑视讯都不累了？
没办法，只能这样。像电机他们后来非要就要写这个。Spice。
我觉得你也厉害了，我觉得我骑到门诺一个礼拜2趟，我觉得我累了。你这样每天骑2趟，来回。
对啊。
累了。
我有时候开车啊。
开车比较不累吗？
对啊。
开车比骑车还不累。
没有，也是要爬出，只是它里面的那个 module 就是它里面的东西要先设定。就我忘记他们是 VLSI 实验还是 K 的实验了，其中一个就是要设定它的通道的长度跟，然后就之类的烂档在上面设定。你说这个应该不会吧？这个它只是跟不太有这个东西。像 Road 它应该就是只有那个刚刚assign的那个，我们要写一个assign，那现在应该不用写。有看黄若琳过成大一节。
出来了。
对啊。
啊你呢？有过吗？
我没有报，我看到他过，我有点后悔没报。
笑死。
因为我没预料到前面的那么多人报，台青教那么多人报。
因为大家都想往北部走啊，没有想在哪。
对啊。今年不知道从哪里生出一堆人。
星期24号。上礼拜五是几号？21。
徐向庭跟那个薛祖恩也有。
徐向庭。
对啊。
他大四。
徐向庭不是国际组的。
是吗？我没说，我记错了，我记错了。
然后看徐向庭 CPE 4题，爽。因为我班上是那个4个 input 跟那个，然后 gate 的layout。
什么东